Hello viewers, welcome to another session with me. You are welcome to Master Builders Online Academy. You are welcome, you are welcome, you are welcome, you are welcome. If you are new in this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. Don't forget at the end of watching this video to like this video, share this video, and make your necessary comments. Now, lest I forget, I stand to remind you guys our policies. Anytime you are set to watch our videos, do not skip any part of the video. This will do you really good. And also, anytime you are set to watch and to learn new concepts from Master Builders Online Academy, do not welcome any form of distraction. Guys, this is for your own advantage. And if after watching this video, you have questions to ask, guys, you have the singular opportunity to replay the video over and over and over again until you get the maximum values that we release in this content. And also, if after replaying the video over and over again, you have questions to ask, guys, do not hesitate to slide down to the comment section and make your questions known to us. We will give you befitting answers to every question that you will drop at the comment section. Generally, we are out here to answer your questions. So feel free to ask your questions. Now, guys, in this lesson, I'm going to be holding you by the hand and walk you through the process of deriving major formulas in fluid mechanics. Yes, you heard me right. In this video, we are going to be looking at a minimum of 6 formulas, derivation of 6 formulas in fluid mechanics. Generally, we know that fluid mechanics is actually an aspect of engineering that deals with the behavior of fluids, either at rest or in motion. And as such, there are so many mathematical models, so many mathematical formulas, so many mathematical relationships that are possible in fluid mechanics. So specifically in this video, we are not going to be solving problems with values. Rather, we are going to be deriving formulas. We are going to be deriving models using first principle. So guys, without wasting much of our time, let's slide to the first section of this video, where we will be looking at the derivation of Pascal law. Now guys, we have the very first part of this derivation of the law. Now we are asked to derive Pascal law for pressure at a point in a fluid at rest. Now, generally, the first thing you are supposed to do is to know what Pascal law is all about. Now, in fluid mechanics, Pascal law is actually defined in reference to fluids at rest. And what does this law state? Pascal law for pressure at a point in any fluid at rest states that such fluids have equal pressure in all directions. And now we know that in physics, generally in science, we have plane, we have space. For plane, we have 2 directions, which is direction x and direction y. But for space, we have 3 directions, which is direction x, direction y, and direction z. So in this regard, we are going to be making use of a space structure. And we know that for a fluid to be at rest, it must be conveyed with a vessel. And such vessel can be of any geometrical shape. It can be circular, it can be rectangular, it can be triangular. But in this lesson, we will make use of a triangular section which actually reveals the x-axis, the y-axis, and the z-axis. So the first thing you do is to say, consider the figure shown below. A section. Now it has a cross-sectional area. It has a cross-sectional area. It has a cross-sectional area. Now in the vertical direction, we have a pressure acting on this end. For the horizontal direction, we have a pressure labeled as P2. And for the inclined direction, we have a pressure labeled as P3. Now guys, there we have the angle of inclination of this third member. So similarly, if this is considered as section 1, I will have this guy to be A1. If this section is considered as section 2, I will consider this guy as A2. And if this end is considered as section 3, I will equally consider the area of this section as area 3. This is the first thing you need to do. Now, the next is you are to resolve this pressure that you have here. And we know that in resolution of forces, you don't resolve pressure. Why? Because pressure is not a vector quantity. Vector is a scalar quantity. We only resolve vector quantity. So in this wise, we are going to find a relationship between pressure and another vector quantity that can be resolved. And we know that force is a vector quantity that can be resolved. And there is a relationship between pressure and what? Force. So all we need to do now, the first thing is we have pressure. P is equal to force F all over area A. So by this we have P is equal to F over A. Now when we make F the subject of formula, we have that F is equal to PE. Now let's assume we call this equation 1. So this becomes our first model. Relationship between force and pressure. Like I just said now, you cannot resolve pressure. You can only resolve force. Therefore, we then look for a relationship between pressure, which is a scalar quantity, and a vector quantity, so that we can resolve the member forces, so that we can resolve this system with reference to the force. So now, looking at this model, if this is P1, similarly, I will have that my F1 would have been what? P1 multiplied by A1. Now, if this is F2, pressure 2, therefore force 2 would have been what? Pressure here multiplied by the area here. Then we have P2, A2. Then finally, F3 would have been what? Pressure here multiplied by the area where the pressure is acting. Then we have P3, A3. Now we can resolve these forces. To resolve these forces, all we need to do is to extend the line of action of these forces so that they can be acting at a point. So when we extend the line of action of these forces, we will have something in this nature. This will have the what? F1, F2, then F3. Now when we transfer this angle, it therefore becomes a relationship between F3 and Y direction. To resolve these active forces at a point with reference to X axis and with reference to Y axis. So all we need to do here is to have sum of Fx is equal to 0 using the equations of static equilibrium. Now, if I resolve these forces along S axis, of course we know that in coordinates, this is positive side of X and this is negative side of X. This is positive side of Y and this is negative side of Y. So it therefore shows that any force that is acting towards the right is going to be taken as positive for X, and anyone acting towards the left is going to be taken as negative for X. Therefore, when we have that F1 is acting to the positive direction, then it becomes a positive. Then minus. Now remember that this force is acting in the negative direction, because if we resolve this, we bring down the tail of this member to align with S axis, the arrow will be facing the negative direction. Then this becomes F3 sine theta is equal to 0. Therefore, mathematically, we then have P1, A1 minus P2, 3, A3 sine theta is equal to 0. This is it. So we call this equation 2. Then also we resolve this system again with reference to resolving this along y-axis. We have sum of Fy is equal to 0. In the same vein, this guy is vertical and is acting upward towards the positive side. That means F2 will be taken as positive. We have F2. Then for this guy, which is F3, when we resolve this, align this member to the vertical direction, the arrow will be facing down, which means it's facing the negative direction. Then that force will be taken as negative. Then this will have given us F3 cos theta. Why are we using cos theta for sum of Fy? Because the angle lies with y-axis. So anytime the angle lies with y-axis, you resolve x using sine and resolve y using cos theta. I think this is clear. Now, equal to 0. Then what is F2? F2 is P2, A2 minus P3, A3 cos theta. Equal, this is equation 3. All we just need to do now to verify the Pascal law of pressure is to ensure that we replace cos theta and sin theta. Now, when we come to this session, we have that this is this figure that we have. This we call A1, this we call A3, this we call A2, and this is the angle. So from this figure, we are going to deduce the value for cos theta and the value for sin theta. Now, sin theta is equal to opposite over adjacent. Now, this is the opposite. The line that is facing the given angle. While the hypotenuse is the longest side. Therefore, we have A1 over A3. Then what about cos theta? Cos theta would have been what? Adjacent over hypotenuse. So this is the adjacent, which is A2 over A3. Then all we just need to do is to come to equation 2 and substitute for sine x. That's all. So therefore we have from equation 2 we have A1 minus P3 A3. Now what is sine theta? We said sine theta is A1 over A3. We have A1 over A3. And this is equal to 0. So from this end, this guy takes care of this guy. We have P1, A1 is equal to P3. When minus P3, A1 crosses the sign of the equality, it turns to the opposite sign. So minus becomes positive. Now when I divide both sides by A1, A1 cancel A1, P1 becomes P3. Then the next is the what? Also substitute for cos theta in equation 3. So we have that from equation 3, we have P2, A2 minus P3, A3 cos theta is A2 over A3 equal to 0. So from this end, A3 cancels A3. Then we have P2, A2. Now, when we connect like terms, we're going to have P3, A2. This guy takes care of this guy, therefore have P2 is equal to P3. Therefore, P1 is equal to P2 is equal to P3, which verifies Pascal law of pressure. What Pascal is trying to say here is that the pressure in S direction, the pressure in Y direction, and the pressure in Z direction is the same, provided that the fluid is at rest. So whenever a fluid is at rest, the pressure in any direction acting on that fluid is constant or true. It shows that if I have 10 bar acting in S direction for a fluid at rest, I will equally have 10 bars in Y direction and even in Z direction. So this is what we are asked to show, that the pressure 1, pressure 2, pressure 3 is the same for a fluid at rest. Pascal law verified. So guys, at this point, if you are yet to subscribe to this YouTube channel, do consider subscribing to our channel. ensure you turn on the post notification bell for more exciting videos. Like I do always tell you guys, when you understand principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. So very quickly, let's look at the next model, model 2. Hello viewers, welcome back to part 2 of this fluid mechanics derivation of formulas. On the board we have model 2. We are asked to derive the expression of variation of pressure with depth. What we are actually asked to look for is that we should show that P is equal to rho GH. This is the pressure with variation with depth. Now, how do we get this done? The first thing you do, guys, is to consider a cylindrical section. Like I explained earlier, a fluid cannot be conveyed without a vessel. So you must consider a vessel of any form, whether plain or solid. Now, in this lesson, we will be taking solid, and we are going to consider an elemental section of a cylinder. Are you there? So if you look at the board now, we have consider a small cylinder of length AB, inclined at angle of theta as shown below. This is the force. So this is the cylinder that we have. And now this is the neutral axis. Generally in science on its structures, we know that forces act at the neutral axis or at the centroidal axis of any geometric property. Now this is the geometric property, which is a cylindrical section, and this is the neutral axis. This is the center, where this is where the forces are acting. Now, for this object, this small cylinder, it is suspended above the ground level. So this is the ground level, which we have taken as the datum. Now, from the ground level, the lowest end of this cylinder is Z. Now, from the ground level, the upper end of this cylinder is Z plus change in air. That is to say, if from here to this end is Z, now from here to this other end is change in Z. So when we sum up these two guys, we have this. So from the lower end or the lower limb, we have Z, and from the upper limb, we have Z plus change in Z. So we have been able to define the elevation of this cylindrical object that is to convey a fluid at this respective distance from the ground level. Next is that any object that is suspended above the ground level, scientifically, we know that such objects are being influenced by gravitational force. Therefore, we have a gravitational pull on this object, which will actually result to the weight of the object. Hence, the object has a weight of W acting vertically at the section. Now, this weight of the object, because the object is inclined, it has an angle less than 90 to the lower limb. And then, so we have an angle, which is an acute angle. While the other end is an what? Obtuse angle, angle greater than 90. But for this guy, it is an angle less than 90. Then we will go with this angle less than 90. This is it. Now, at the neutral axis, we have forces acting. So if I have F1 acting at this entrance, this end, then I have F2 entering at this other end. And looking at these forces that we have here, we find out that both are compressive forces. Remember earlier I stated that it is impossible to resolve pressure because pressure is a scalar quantity. And scientifically, we don't resolve scalar quantities. We only resolve vector quantities. Why? Because scalar quantities are without direction. They only have magnitude. So we only resolve those quantities that have both magnitude, or not only magnitude, but they equally have direction. So any quantity that do not have direction cannot be resolved. So in that light, pressure is one of those quantities that do not have direction. And this is one of the reasons why we don't resolve pressure. And therefore, we now find a relationship where pressure relates with another vector quantity that can be resolved. Then, so we have pressure multiplied by A would have given us force. So indirectly, we have this guy here as a force. Similarly, we have this guy here as a force. So at the first end or at the entry end, We have P multiplied by the area. Now, why are we making use of changing A? We are using changing A here because this section is an elemental section, and I explained earlier that we are using first principle. And anytime you are using first principle, all you normally do is to take a small portion of the whole section. So if this is a cylinder, we just took a small part of the cylinder. Let's assume this is the shaded portion. This is what we just took. This is the cylinder, alright? This small section here is what we take. So everything here, this will be changed in area, while this also will be changed in length. So that elemental section we take is what we have as this. But we just magnify it so that we will be able to relate this, we will be able to reveal all the active forces. So in this case now we have the pressure acting at both ends, and these pressures, they are acting compressively. Are you there? And now I have explained that this guy is in force, in terms of force already. This guy is also in terms of force. So the first thing we are quickly going to do here is to resolve this system. That's it. And to resolve this system, we will consider that this is X and this is Y, inclined. Now, generally in science, we have what we call global coordinate and local coordinate. Are you there? This is global coordinate. But when you have something like this is local coordinate. So I want to use local coordinate to resolve this system. So in using local coordinate system now, it shows that this line here, this line of action, which is our neutral axis, will now be taken as X, while this guy that inclines this way will be taken as Y. So if I am resolving the forces now, this guy is purely X, this guy is equally purely S, but this guy is inclined. Or otherwise, you can decide to rotate this system. Now, if I decide to rotate this system now, I will have something like this. I have a force acting at this end, I have another force acting at this end, then I have the load, the weight. So if I resolve this, this is X, then this is inclined. The same thing I'm doing here. So you can decide to rotate this so that you will convert it to the global coordinate, or you leave it like that so that you can use the local coordinate system. So now I want to make use of the local coordinate system, and that's the reason why I have indicated this guy. Are you there? So now, making use of the local coordinate system, we have already defined that this is X and every other would have given us Y. Then if we resolve this system along S, sum of Fx is equal to 0. And now we are going to have this guy is acting to the positive side of X, just as if I rotate this guy, P changing A, and P plus changing P multiplied by changing A. So this guy is acting to the positive direction, which will give us positive. But this other guy is acting towards the negative, which will have given us minus P plus changing P multiplied by the changing. Then, for this other guy, this is the direction of the arrow. So when we resolve this member, it's equally acting towards the negative direction. Then we have this as minus W cos theta equal to 0. So what we need to do now is to simplify this. Why we have this as P changing A, when we expand this guy, this will have given us P multiplied by changing A and minus changing P multiplied by changing A minus W cos theta equal to 0. So this first guy, we eliminate this guy. And we have minus change in P, change in A is equal to W cos theta. Who will call this equation 1. Now, the next thing we are quickly going to do is to obtain the value of W and cos theta. What will be the value of W in terms of these geometric properties? Now, we know that W, which is weight, is equal to mass times acceleration due to gravity, or mass multiplied by acceleration due to gravity. And we equally know that mass is equal to what? Density multiplied by volume. You know that density is equal to mass over volume. So when I make mass the subject of formula, this is what I will have. So in place of M, we are going to replace this guy with rho g. Therefore, we have that weight is equal to rho v multiplied by g, which this is equivalent to rho g v. Now we know that this section is an elemental section. Now, what will be the volume of this elemental section? The volume of this elemental section will have what? Length multiplied by the area, and the length is the L, the area is the A. So we equally have that V is equal to change in area multiplied by change in length. This will become that V. So in place of V, we are going to replace it with what? The visible parameters that we have in this section. Of course, there is no volume here directly. We do not have V represented here. But we have the change in length, and we equally have the area of this section. So when we multiply area by length, we have volume. So this volume, we will replace it with this guy. Therefore, W would have given us rho G, change in A, change in L. We will call this equation 2. We have obtained the value of the weight in terms of the properties that is here, which is in terms of the material property and the geometric properties. These first two guys are the material properties. These last two guys are the geometric properties. Are you there? Now, if this is understood, then the next thing is, how do I obtain cos theta? Because we equally need to replace this cos theta. Now, I can draw this sketch. Now, remember that if this is an inclined line, from this end to this end, I can reduce it a right angle triangle. So I have a right angle triangle. This is the length, the L. Now, from this end, like we have here, from here to this end is dz. So we have this as dz. And the angle, which is this angle is what? Corresponding to this angle. That means this guy is theta. So here we have angle. How do I find cos theta from here? We have that cos theta is equal to adjacent over hypotenuse. Is that correct? Now this is the adjacent. This is the opposite. The line that is facing the given angle. Then this is the adjacent. This is the hypotenuse. So we have change in Z all over change in L. So we can equally call this equation 3. All we just need to do now is to substitute equation 2 and equation 3 into equation 1. Then we are done. Now let's use this expression. Hence we have minus change in P, change in A is equal to W. We'll replace this guy. W is rho D, dA, dL multiplied by cos theta, and cos theta is dz over dl. Dz over dl. Now, this guy takes care of this. Now we have change in P, change in A is equal to rho D, change in A, change in Z. Now, when we look at the left-hand side and look at the right-hand side, we discover that the elemental area is common. So what do? All we simply need to do is to divide both sides by changing A, which is the elemental area. And when we do that, we have that change in pressure minus change in pressure over change in A, all over minus change in B is equal to rho G, change in A, change in Z, all over negative change in A. So this guy takes care of this guy takes care of this guy. We have negative change in P is equal to rho G change in Z. Now, at this point, for us to be able to get the actual value of P, all we simply need to do is to integrate with respect to P at the left hand and with respect to Z, which is the variation of depth at the right hand side. Therefore, we quickly introduce our integral. Now we have this negative. So when we introduce our integral, we have change in P is equal to integral of change in Z. Now, when we integrate this guy with respect to P, we will have P. And when we integrate this other guy with respect to Z, we will have Z. Just the same way if I have integral of dx, which is written as 1 dx. If I integrate 1 ds, I have x. If I integrate 1 dy, I have 1. So if I integrate dz, then I have z. That's all. Now, at this point, we understand that our assumption was above the ground level. And we know generally that when we are talking about depth from a certain height or beyond a particular height, So if that is taken, therefore it shows that H is always what? Negative of the height. Then we have that record. At this point we recall that H is equal to negative Z. Then I have P is equal to rho G negative Z. Then I will replace this negative Z with H. Then we have P is equal to rho G H. This is the variation of pressure with depth that we are asked to show in this question. It is very, very simple. Very, very simple. Like I said, all you need to do is to know principles. When you understand principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. So, guys, if you are given this to resolve, it is as simple as this. So, see you guys as we begin to prove model 3. See you guys in the next part of this lesson. Hello viewers, now we are in part 3 of this mind-blowing derivation session. Now we have model 3. We are asked to derive the expression for the rate of change of momentum of a fluid between two sessions. Very simple. Derive the expression for the rate of change of momentum of fluid between two sessions. This is a fluid again. There cannot be fluid without a conveying vessel. So in this session now, we are going to be looking at a vessel that have an entrance and an exit. So let's assume that this is the session with thick line. This is the session. Okay? A, B, C, D. Now, this vessel is containing a water or a fluid of any type. It's containing a fluid or containing fluids of any type. Now, if we have an elemental change of position from point A to A prime, we have an elemental change at this session. We equally have an elemental change at the right session at point C and at point D. So you have C, C prime, D, D prime. Now we need to know the sheet at this point. What is the distance between C, C prime, D, D prime, or A, A prime? What would have been the separation between these 2 points? What would be the separation between these 2 points? We are quickly going together. Now, assuming this is the entrance where we have section 1, we have Q1, A1, and velocity. Because for every fluid that moves, there must be speed of flow, rate of flow. So Q is the rate of flow, A is the area of this section at the entrance, then V is the velocity of the fluid at the entrance. Then these are the exit. Then we have Q2, A2, V2, which is rate of flow, area, and velocity. Now, all that we need to do is to focus on this elemental sheet, not this main section. Similarly, at this section 1, we will focus on this elemental sheet. So all we really need to do is to get the mass of this section and the distance. Now we know that momentum is equal to mass times velocity. So we need to find the mass of the quantity of water contained here, the mass of the quantity of fluid contained here, and of the fluid contained in this section. Are you there? So now how do we get this done? The first thing is we record that mass M is equal to density multiplied by volume. Are we there? This is it. So this is mass. Rho V. Now the next thing we are quickly going to do at section 1, what is the volume? At section 2, what is the volume? Now we are going now to obtain the volume, we will multiply the distance covered by the area at the entrance. Similarly, at this other end, we will equally multiply the area here by the distance to get the volume. So how do we get the distance from C to C prime? All you need to do is to understand that distance is equal to velocity multiplied by time, or velocity is equal to distance over time. So when I make distance the sort of formula, that means I would have had my distance to be what? Velocity multiplied by time. Then this guy becomes V1 multiplied by T. Then this guy also becomes V2 multiplied by T. V2 multiplied by T is the distance between A to A prime, which is similarly between B to B prime. While V1 multiplied by T is the distance between C prime, and D prime. We have already gotten the distance. Now, to get the volume here, we need to multiply the area at this entrance. This is 2. This is section 1. This is section 2. So we quickly multiply this distance by the area to get the volume. Therefore, mass of A prime and B to B prime, we'll take this as M1. And M1 would have given us density multiplied by what is the volume. Now, like I explained, volume would have the area at this entrance, which is A1, multiplied by what? Distance. V1, T1, which is velocity 1 times. This is the area. This is the volume. This is distance. This is the area. Therefore, M1 would have given us rho V1, A1, T1. We can call this equation 1. Then similarly, the mass of C prime and D prime is equal to M2. So we have M2 would have given us the density multiplied by the area. The volume here would have the area of this section multiplied by the distance. Then we have A2 multiplied by V2 times. This is the volume for this exit. Then when we multiply this guy out, we have rho V2 A2 T. This is equation 2. Now, the next thing we are quickly going to obtain is to obtain the momentum at section 1 and at section 2. Now that we have gotten the mass, and we recall that momentum M is equal to mass times velocity. Mass times velocity. So, if I am obtaining the momentum at section 1, I will label this as M1. And if I am obtaining the momentum at section 2, I will equally label M as M2. Therefore, momentum section 1, M1 would have been what? Mass 1 multiplied by velocity 1. And then we have M1 is equal to, what is mass 1? Mass 1 is rho V1 A1 T multiplied by V1. So when I multiply out this guy, I have rho A1 V1 squared T. We will call this equation 3. Similarly, we will equally obtain the momentum in section 2. So we will call that M2. Now we have this guy to be what? M2 momentum. M2 momentum in M2 would have given us mass 2 multiplied by velocity 2. Now, therefore, we have the momentum in section 2 will be equal to what is M2? Equation 2. M2 is density, volume 2 multiplied by area 2 multiplied by T, then multiplied by this second velocity. And when we multiply this guy out, we have rho A2 V2 squared T. This is equation 4. Then the next is to obtain the change in momentum, because the question says that we should find the rate of change of momentum. So now let's obtain the change in momentum. And what is change in momentum? Which is the difference between the entry and the exit. Is that correct? So we have change in momentum. We have this as delta M. This will have given us delta M is equal to M2 minus M1. Final minus initial. Don't forget this is the entrance. This is the exit. So we are going to have it as exit minus entrance. That will be the difference. Final minus initial point. Now, if this is understood, what is capital letter M2, which is our momentum? We have this to be rho A2 V2 squared T minus M1 would have given us what? Rho A1 V1 squared T. Now, when we look at this critically, we see that rho T is common. So we factorize this guy. We have rho T into A2 V2 squared minus A1 V1 squared. Now, at this point, we recall that the rate of flow of any fluid is given as Q, is given as what? A multiplied by what? V. Which is the same as if I have this as Q1, this will give me A1, V1, and if this is Q2, I will equally have this as A2, V2. So here, if I have this guy to be A2V squared, this is exactly the same thing as A2 V2 dot V2. So I can replace these two guys with Q2. Similarly for V1. Automatically, we can have this equation as change in momentum is equal to density multiplied by time. We will have this as Q2. Only one V2 will be left here. Then for this guy, if I remove one V1 from here, this will give us Q1 V1. This is the change in momentum. Now the question says the rate of change, and we know that rate is anything divided by time. So to find the rate of change of momentum, we are quickly going to divide this guy by t. Then we get the final answer. Now, rate of change of momentum. We have this as change in m over t. That's what it means. Therefore, we have rho t into Q2 V2 minus Q1 V1 all over t. And when I divide this guy, I have rho into Q2 V2 minus Q1 V1. This is the answer to this question. So, the expression for the rate of change of momentum of a fluid between 2 points or 2 sections is what we just obtained as this. So, like I said before, the first thing you always need to understand is principles. When you understand principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. We have successfully proven equation 3 for this lesson. Now, like I said earlier, we have 6 models to derive in fluid mechanics. We have derived the 3rd one. Now, guys, I will see you in the next class where we'll be looking at part 4 of this derivation lesson. See you guys in that class. Hello viewers, welcome back to another session with me. If you are new in this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. Don't forget, this is a continuation lesson. On the board, we have model 4 in our series of teaching. Now we are asked to derive the expression for the hydrostatic force and the center of pressure on a surface immersed in a liquid. This is very simple. This is fluid mechanics dealing with the properties of fluid. Now, if this is taken, then this is a datum. Let's assume this is the surface of water. Yeah, this is the surface of water, O to O. So everything here, this is the body of water. Now, this is the object that is inserted inside the water, that is immersed inside the body of the water at an inclined angle. Are you there? Now we are asked to find the hydrostatic force, which is this force acting at this end, and the depth of pressure, which is same thing as H prime. So what we are actually looking out for in this question is F and H prime. Very simple. So now this is the session. Now what we do is, since we know that we are using first principle to derive. Like I explained earlier when we started, I mentioned that all the provings that we are doing here, or that we are going to be proving, we make use of first principle. And in making use of first principle, when you have a large session, you just take a small portion of that particular session. Now we have taken a small portion, and the force acting on this session is change in F, just small force. Similarly, this session we also have change in area. Also have what? An elemental area called changing A, delta A. Now this is it. Therefore, from this point to O, we have a distance of y. And the vertical depth of this point is h. Now, this whole section have a center of gravity, which is the middle point. Now, this is the middle section of this whole rectangular or cylindrical section. Now, the center of gravity from O is y bar, while the vertical height is h bar. Just the same way you have x bar or y bar when you are finding first moment of area, second moment of area, or you are obtaining centroid. So this is the centroid. So for this section now, this is the vertical distance and this is the inclined distance. While for the center of pressure at this point where the hydrostatic force, which is the force due to what? The force of water, are we there? Acting on this body. The force of water acting on this object is at this point. And it is at a distance of y prime from O, while the vertical depth is h prime. And like I explained earlier, we are looking for this guy and looking for this guy based on this question. And is that there is always a relationship between force and pressure. And to obtain the relationship between force and pressure, we recall that pressure is equal to force over area, which is same thing as P is equal to F over area. Now that we are considering the elemental section, like I said now, the force here is changing area, and this guy is also changing area. So now we are not going to have change in pressure because this object is at rest, and for any fluid at rest, the pressure is the same. So we are going to use the actual pressure because the pressure remains the same in as much as this object is at rest, or the fluid in question is at rest. Hope you understand this step. If this is taken, therefore for this elemental section, the pressure acting there will have been changing F over changing A. Now when we make change in F the subject of formula, when we have that change in F is equal to P changing A. Now this is it. We can call this guy equation 1. Now for equation 2, when we replace pressure, we know earlier on that pressure is given as rho g h. All we need to now is to replace pressure with rho g h. Therefore, we have change in F is equal to rho g h change in area. Now, for us to be able to obtain this force, we need to integrate. So when we integrate this section, when we introduce our integral, we have change in F is equal to integral of rho g h change in A. When we integrate F, when we integrate dF, we have this as F. This is the hydrostatic force, which is equal to rho d integral of h dA. Now we understand that is the same thing as first moment of area. And when we integrate this guy, we will have this as A bar square. This is it. So this guy is first moment of area. So when we simplify this, the outcome is this. So anywhere we have this guy in this equation, we will replace this with this. Then we have F is equal to rho g into A multiplied by h bar. And when we multiply out, the hydrostatic force will have been rho g A h bar. Then F is the same thing as what? Specific gravity A h bar. This is the hydrostatic force, where this guy is density times acceleration due to gravity. Therefore, the hydrostatic force. F is equal to rho G A prime, which is equivalent to this A prime. This is the hydrostatic pressure. Hydrostatic force. This is the hydrostatic force. F is the hydrostatic force. Rho is the density of the fluid. G is acceleration due to gravity. A is area of dissection. Then H is the what? Center of gravity of any section that you are given at all. So the next thing we are quickly going to do is to obtain the center of pressure, which is H prime. And to obtain this, all we simply need to do is to take moment about O. About O, we have this guy multiplied by this distance. Moment is force multiplied by perpendicular distance. Similarly, we have these two forces acting here. Therefore, we have taking moment about O. We have F. What is the perpendicular distance of this force from O? We have it to be what? Y prime. Then we have F multiplied by Y prime is equal to, now we know that this is a full force, but this guy is an elemental force. So for us to convert this elemental force to a pure or a full force, we will introduce the sign of integral, so that when we integrate, we know automatically this will turn to force. So we have this as integral of dF multiplied by, what is the distance of this force from O? That is Y. We have this multiplied by Y. It's as simple as this. Then the next thing we are quickly going to do is to substitute for this guy, which is the F. We know that the F is equal to integral of rho G H du A. And equally, F is equal to rho G A H prime. We already know this. So in place of this guy, we will put this. In place of this guy, we will put this. But let's suspend this guy for now and substitute for what? dF. Now we have this as F multiplied by Y prime is equal to integral of rho G H dA multiplied by Y. We come to this end. Now from this sketch, we have a triangle, which is from this end to this end. So we have this as H and we have this as Y, theta. So we have something of this nature. This is H, this is Y, and this is theta. What is the relationship between Y and H? That would have been what? Sine theta. Sine theta. This is opposite, this is hypotenuse. So we therefore have that sine theta is equal to opposite over hypotenuse. Now from this end, when we make H the sort of formula, we will have this as Y sine theta. So in place of H in this model, we will put in Y sine theta. Therefore, we have F multiplied by Y prime is equal to rho G integral of Y sine theta dot dA Y. Now, when we simplify this further, we have that F multiplied by Y prime is equal to rho G sine theta integral of Y squared dA. Now, integral of Y squared dA is the second moment of area, which is equally known as moment of inertia. Are you there? So all we simply need to do now is to replace this guy with the equation of what? The second moment of area. Then we have, recall that integral of Y squared dA is equal to I naught, and I naught is equal to K naught squared. When we further express this guy, we know that K naught is equal to Kg plus the centroid. And now, if this guy is squared, then we have K naught squared is equal to Kg squared plus h bar all squared. So like I said earlier, when we integrate y squared dA, it is second moment of area. And that second moment of area is equal to what? I naught. Y, which is equal to what? A k naught. This k is the radius of gyration. The radius of gyration. And this guy is given as kg plus h bar. And when we square this guy, we will equally square the right hand side of this expression. Then we have f multiplied by y bar is equal to rho g sine theta dot I, we call this guy equation 3. Let's assume we call this guy equation 1. Then we call this other guy equation 2. Now this becomes equation 3. At this point, the next thing we are quickly going to do is to replace this guy. The depth of what? The neutral axis. Are you there? So if this is the distance from O, now what is the vertical distance of this force? We call it center of pressure. So to obtain the center of pressure, we will also draw a right angle triangle with relationship between what? H bar and Y bar. And this would have given us instead x. This would have given us Y prime, and this is H prime. This is theta. Now, when we find the relationship between H and Y, we find out that it's sine theta. So sine theta here would have given us what? Over Y prime. And now we are looking for this guy. So we want to make Y prime the subject of formula. When we make Y prime the subject of formula, we have Y prime is equal to H prime all over sine theta. Then in place of this guy, we have F multiplied by H prime over sine theta is equal to rho g sine theta multiplied by. Now we want to quickly replace this guy with k naught squared as defined here already. Are we there? Then when we cross multiply, we have f multiplied by h prime is equal to, when sine theta multiplies this end, this will have given us rho g sine squared theta multiplied by a into, what is k naught squared? We said that k naught squared is equal to kg squared plus h bar squared. So we have this as kg squared plus h bar squared. This is all we've done so far now is to what? Cross multiply here. We have this guy and replace k naught with what we have in equation 2. Now let's make h bar the subject of formula. If we make h prime the subject of formula, we have this as rho g sine squared theta a into kg squared plus h bar squared all over f. And what is the value of f? We know that the value of f square theta a into k g squared plus h bar squared all over rho g a bar. So at this point, rho g takes care of rho g, a takes care of a. We have this guy is equal to sine square theta into kg squared plus h prime squared, h bar squared all over h bar. So all I need to do now is to open the brackets, multiply through by sine theta. So when we do that, h prime would have given us kg squared sine square theta plus, now when we multiply this guy by this, we will have sine square theta h bar squared. But we know that this guy is perfectly vertical, and the angle that this guy made with the horizontal line is a straight line, which is angle 90. So when we put in theta as 90 here, sine 90 would have given us 1. 1 square would have given us what? 1. Therefore, the answer to this, when we multiply this guy with this guy, we will still have this guy squared all over H bar. Then finally, all we simply need to do is to divide. We have this guy is equal to kg squared sine theta all over H bar plus, when we divide this guy by H, we have H bar. This is the equation that we are asked to look for, where kg squared, kg is equal to Ig over A. Very, very simple. So now, all you just need to do at this point, like I explained, when you multiply this guy by this, you have this. But when you multiply sine square by this guy, because this member or this depth is making angle 90 with the horizontal, you put in theta as 90. So sine 90 is 1. 1 square is 1. And 1 times this h bar square would have given us h bar square. Next is to what? Divide the numerator by the denominator. We have this, and divide this guy by the denominator. We have this. Now we can substitute for kg squared so that we can have this reduced to some extent. So at this point, guys, this is what we are asked to look for. So the center of pressure on a plane surface immersed in a liquid is given as this. Now, guys, if at this point you are yet to subscribe to this YouTube channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. Now, guys, we have ended model 4. We want to quickly look at model 5. See you guys in that session. Hello viewers, welcome back to this session. We want to start looking at model 5. Now on the board we have model 5. We are asked to derive the Bernoullis equation of steady state flow. The Bernoullis equation for steady state flow. This is very, very simple. And in proving this, a cylindrical section is equally taking an elemental section, because this is a fluid, and to convey a fluid, a vessel is always required. Now in this derivation, we are making use of first principle. Now when we look at the board, we are asked to derive the Bernoullis equation of steady flow, state flow. Now we have solution. Consider the forces acting on the elemental fluid below. This is the section, or this is the conveying vessel, this is the entrance, this is the exit. This can be the exit, while this other end is the end, is the what? Entrance. Are we there? Now at this point we have a force, a pressure here, and at this other end we have another pressure here, which is P2, while this guy is P1. Then the distance of this elemental section is changing x. While the weight of the object, because it is suspended above the ground level, this is the ground level, which is the datum. We have the weight of the object as W, which is mass times acceleration due to gravity. Then at the lower end, we have the depth as Z, which is the elevation. And from the other end, we have the elevation Z to be 1. Now at this end, we have the area at this entrance end as area plus change in area. Because when we look at this area here, we find out that this guy is wider than this guy. So if this is area, this is velocity, and this is pressure, that means when you move from this end to this point, it has increased. So what the changes that we have is what we added to the original area to get the area at this point. The changes that we have is what we added to this velocity to get the velocity at this end, and the changes that we have is what we add to the pressure to have the pressure at this end, because of the fact that this end is larger than this end. So if this is A, this must be A plus something. If this is V, this must be V plus something, additional value. And if this end is P, then this pressure here will be more. So what is that elemental value? It can be more or less. Are we there? So this is it. Now this is the section. Then we have the surface. Now in this system, we have 3 active forces. One is the one acting on the surface. The other is the one acting on the string tube, while the other is the weight of the vessel. And the sum of all of these 3 forces must be equal to what? 1 second force. So now we need to quickly obtain what is the force acting on the inclined surface. What is the force acting on what? The string tube. And what is the force that is acting, or what is the force that equals the weight of this cylinder or of this vessel? Now all we need to do is to take the first one, F1. So like I defined it now, F1 is the force acting on the surface. And that force acting on the surface would have been pressure multiplied by area. So now understand that since I have this section as elemental section, then the area will equally be what? Change the area for the surface. This is the elemental. So I have elemental distance to elemental area. Are we there? So this will have given us. Now understand that if the pressure acting at this point is P plus change in P, the pressure acting on this surface is P plus half of this pressure, because before you move from this end to this end, it has increased to this maximum also. At the surface of this, we are going to have half the change in pressure. Therefore, we have P plus change in pressure over 2, then multiply by what? Change in area. And this will have given us, when we multiply out this gives us P change in area plus change in P change in area all over 2. And now understand that anytime you are using first principle to prove or derive any model, when two elemental values multiplies each other, the value tends to 0. Automatically, the product of change in P multiplied by change in A is already 0. Therefore, F1 is equal to P change in A. We will call this equation 1. Now, the second force, which is F2, is the force acting on the string tube. The force acting on the string tube. And in this case, we see that the string tube, we have this and we have this entrance. We have this entrance and we have this. Now, from this end, we have P multiplied by A. That is the pressure, the force that we have here. Then minus the one that we have at this end, because one is entering, the other is leaving. So it shows that we are going to find the difference. Then, what is the force at this point? It will be pressure here multiplied by the area here. Then the pressure there will have P plus change in P, then A multiplied by what? Change in E. This is it. Now we need to expand this expression. This would have given us PA. Now remember, we are using expansion of brackets. So P multiplied by A will give us PA, and P multiplied by delta A, P multiplied by delta A, this will have given us negative P delta A. Then we are done using the first term here to multiply the two terms inside the second bracket. Now we want to use the second term in the first bracket to equally multiply the two terms inside the second bracket. And to have this done, we have multiplied change in P by A, we have A change in P. And when we multiply change in P by change in A, this gives us change in P, change in area. So mathematically, the first two terms we cancel out. We have this as negative P change in A minus change in P. And I explained earlier that when this guy multiplies itself, when elemental change multiplies elemental change, because of the fact that we are using first principle, this product would have given us 0. So in this case now, this is what we have. We call this equation 2. This is F2. Now to find the third force, F3 is the weight of this elemental object. And what is this elemental object? What is the weight of the fluid here? The weight of the fluid. Now, if I have a vessel, 20 liters empty vessel, and I fill that 20-liter empty vessel with a water or any form of liquid to the brim, what is the volume of the fluid? It's exactly the same as 20 liters. So now, if I am using any vessel and the vessel is filled to the brim, if I know the volume of the vessel, then I equally know the volume of the fluid it contains. So if I am considering the weight of this vessel is equally the weight of the fluid, because the volume that this vessel is when it is empty is equally the same volume when it is filled. So if the volume of this vessel is 20 liters, the fluid inside when filled to the brim is equally 20 liters. Now, At this point, we have that this is equal to the weight of fluid, which is W. Then F3 would have given us what? W. And W is mg. Now, in this case, we know that mass has a relationship with density, which is rho multiplied by volume. Density multiplied by volume is mass. So in this case, we will quickly replace mass with density, rho g, volume. Now, what is the volume of this section in terms of these properties? So by extension, the volume of this guy would have given us A rho g multiplied by A multiplied by change in A over 2, because it's at the surface. Alright? The fluid is inclined. Then multiply by what? S cos theta. Because if we take the actual angle of this, we find that this surface is inclined. So when we resolve this, this will have given us delta S cos theta. And when we simplify and solve for that, we find out that F3 is equal to rho g. That will have given us A plus delta A over 2 dot this multiplied by cos theta. When we obtain the value of cos theta here, cos theta would have given us negative delta Z over delta X. This is the change in Z. When we take this out, this is hypotenuse, this is adjacent, where we have the angles. Therefore, when we simplify this out, we have that, and this guy multiplies this. Finally, F3 would have given us negative rho. Now, A multiplied by change in Z would have given us A change in Z. Now, this guy multiplied by change in Z would have given us 0, because anytime elemental change multiplies another elemental change, the outcome is 0. Therefore, this would have given us equation 3. Now that we have successfully obtained this, the next thing we are quickly going to do is to understand that at equilibrium, summation of all the forces is equal to mass times acceleration is equal to force. Summation of all the forces acting on this system is equal to what? A pull. And what's that pull? MA. Now, what is M? What is A? We have already obtained that sum of all have given us F1 plus F2 plus F3. This is the interpretation of the summation of all the forces is equal to MA. Let's call this equation 4. What is M? What is M and what is A? That's the next thing. Therefore, understand that M is equal to mass. And mass would have given us density times volume. And density times volume, the volume here would have been area on this surface multiplied by what? This distance. And that area on that surface is A plus change in A over 2 multiplied by what? Change in S. This is how we are going to get the volume on this surface. On this surface. Along the tube. Are you there? Along the tube. That will be the area. Change area plus half of the change in area multiplied by the inclined length. This is it. Now this is equation 5. Now for acceleration, we know that acceleration is change in velocity over change in t. And by extension, this will have given us u change in u over change in x. This is equally the formula for velocity. By replacing t, we have this. Now, the next thing we are quickly going to do here is to substitute MA. Then we call this equation 6. All we just need to do is to substitute equation 6, equation 5, equation 3, equation 1 and 2 into equation 4. So we know that F1 is P change in A. I'll put in the value of F1 plus F2 is minus F2 minus P change in A minus A change in P. Then F3 is equally minus rho G A change in Z is equal to NA. Alright? Now, because of the space, let's suspend this for now. Okay? We'll put in the value of M and A later. Now, if we simplify this end, this will have given us P change in A minus P change in A minus A change in P minus rho G A change in Z, which is equivalent to A. Now, this guy takes care of this guy. We have A change in P minus rho G A change in Z is equal to, what is M? The value of M is rho A plus change in A over 2 multiplied by change in X dot. What is acceleration? Acceleration is U change in U over change in X. Change in S takes care of change in X. Now the next is to expand. Then we have this as A change in P minus rho G A change in Z is equal to, when I multiply this out, I have P rho multiplied by A multiplied by U change in U. Then I have rho A U change in U. And now when I multiply change in A by this guy, it automatically becomes 0. Or we have this as plus rho change in A over 2 U change in U. So change in A multiplied by change in U will have given us this as 0. So we rearrange this guy, we have this as minus A change in P minus rho G A change in Z is equal to rho AU du. Now, when we look at the left-hand side and the right-hand side, we find out that A is common. So we divide all through by A. And when we divide all through by A, we have this as negative change in P minus rho G change in Z is equal to rho U change in U. All we just need to do now is to arrange this guy and equate it to 0. And when we arrange this guy, we're going to have, now if I take these two guys, the two terms at the left hand to the right hand, everything will become positive. Then we have change in P minus rho U change in U. Then everything becomes plus rho G change in Z equal to 0. So we call this guy equation 7. All we just need to do now to get our final answer is to integrate this guy. When we integrate this guy, we will get the equation of flow derived using the Bernoullis method. So now, all we need to do now is to divide both sides by rho G. We want to ensure that the coefficient of the elevation is 1. Are we there? All we need to do is to quickly divide all through by rho G. Then if we do that, we have change in P over rho G plus rho U du over rho G plus rho G dz over rho G is equal to 0 over rho G. Now guys, density cancels density. This guy takes care of this. We have change in P over rho G plus U change in U plus change in Z is equal to 0. At this point, all we just need to do is to integrate. Then we will introduce our integral. When you integrate this guy with respect to P, we have this as P over rho G plus, and when we integrate U with respect to U, we have U squared over 2G, then plus, when we integrate 1 with respect to Z, we have Z equal to, now you understand that anytime you integrate, you always have constant, so equal to constant. K or C. This is the equation for Bernoulli's equation. So at this point, we have this as this. Therefore, this can be P1 over rho G plus U1 squared over 2G plus Z1 is equal to P2 over rho G plus U2 squared over 2G plus Z2 is equal to constant, just continuous. This is it. Now at this point, we have been able to derive the Bernoulli's equation for steady state flow. So if you are given this in exam, this is how you go through the process of deriving the equation of flow by Bernoulli's equation. Deriving the Bernoulli's equation for steady flow rate. So guys, this is the end of this derivation session. Every other derivations we will attend to them in our next lesson. Now, like I do always tell you guys, when you understand principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. It is very, very important that you get to understand the principles that we applied while we were solving these problems one after the other. So in the next video, we'll be using these equations we have derived so far to solve problems with given values. And I know you are going to enjoy that session. We are going to enjoy that session. Yes, I know you will enjoy it. So guys, if you are yet to subscribe to this channel, do consider subscribing to this channel. And ensure you turn on post notification bell for more educative content. Guys, don't forget to like, share, and make your necessary comment. See you guys in the next class.